Hey everyone, so welcome to part 3 of our Basics of R course. We're going to do variables, we'll look at using functions, we'll see how the help documentation works, and then we'll get into some vector indexing. Now, from the last video, you should be able to look at these two different lines of code and without running them, predict for me what they'll produce and whether or not they'll produce any either warnings or errors and why. If you can do that, excellent. Let's keep going. So look at this bizarre command. It's got an A on one side of it, and then it's got an operator. Previously, we've worked with operators like plus, divide, modulo, etc. They all have one character. This one's got the lesser than symbol and then the minus symbol, so it looks like an arrow, and then a 3 on the other end. So it's like it's shoving the 3 into the A, whatever that could possibly mean. So let me just run the A now, and it produces the 3 again. Okay, so it's like the A has become the name of a box in which to put the 3, and that's exactly what a variable is, because that box A, you can put lots of different things in it, so it varies what you can put in it, so it's a variable. Assignment, because I've currently assigned it to A, and we're going to do operations on these variables. So if I just run the name of the variable, it tells you what the contents of the variable is. I can use the variable in regular calculation. So when I run a calculation like this, I get 8 because R has looked at the 5 and the operator plus and said this is an operator that takes 2 numbers. A is not a number, obviously, but Tim, maybe A is the label of a box that contains a number, so it will look inside the box and do the calculation on that. Similarly, A plus A, take a second to guess, correct. I'm going to assign another variable now, so you can see this assignment operator. Again, it looks like you're shoving a thing into another, and it's absolutely possible to do this the other way around as well. Just as a sort of quirk of the language, you can put 2 into B, or B goes into 2. So now that we have that, we can use A plus B, we should get 5, that's right, and we can even define further variables using the consequences of calculations we've previously defined variables. Note, if you try to run a variable that's not yet defined, it will say, hey, well, I didn't know what D was, and so I thought maybe it was a variable, and I went and checked my table of symbols behind the scenes, and I haven't been able to find a D. So variables have to be defined to use them. C multiplied by 3, for example. When you overwrite a variable, it's just the same way as assigning. So B was previously 2, I'm going to set it to 100, but the question now might be, remember when I defined C was defined in terms of A and B. So is that going to update now? Is it like C sort of remembers how it was defined, and it's going to be defined as A, which was 3, divided by the new B, which is 100, and we'll get 3%? No, we get the same value as previously. So C was sort of set at the time. Now that is actually important, and it's something you should think about because it is a choice in a programming language, and there may be times when you want various functions and operators that you later write to behave the other way, where they do update when you change the components that went into them, and that's absolutely possible. And there are other languages that will do that more by default. So it is worth noting, even if it does seem a little bit trivial to point out now. Here's just a party trick in the language. You can define more than one variable with a value. So I've taken the 2 and I've shoved it into a variable whose label is var2, and then I've shoved that value again into a thing called var1. And you can actually run that, and both of those will be defined as 2. It's a party trick. It's just again, some languages allow these shortcuts. Okay, that's the start of variables. Obviously, it's going to get deeper than that, but let's move to now the subject of functions. So you'll remember from the first lecture that this defines a list of numbers 1 to 5. I'm assigning them into a variable called numbers, which seems like a pretty good name for it. So numbers now contains 1 to 5. I'm going to run sum and then some brackets and then numbers. What do I get? I get the sum, 1 plus 2 plus 3 plus 4 plus 5. What you've seen is a function, right? A function is a machine that does some work. Often it takes some input and gives some output. So in this case, it took a bunch of numbers and it gave the output, which is the sum of those numbers. We'll see exceptions to those rules later. And you can always tell a function by the syntax that it has the name of the function and then the bracket, an opening bracket, and then eventually a closing bracket. I can actually do something like this. I can take that word sum and put 4 into it. So now if I run sum plus 1, is it going to be the variable or the function? No, it's going to be the variable. So that label sum is actually being used with 2 different roles, but R can tell which one I'm talking about because of the context of those brackets that I put next to it. So when I put sum with brackets, if I put it with nothing in there, it's decided that that's going to equal 0. Interesting, I didn't know that. It could have equaled null or something, but there you go. So it knows whether you're talking about the function or the variable. In fact, I could probably use both in the same line of code. Okay, so here's just some mathematical functions you use all the time. Length gives you the length of the vector, so a length 5 vector has length 5. Max gives you the highest value, min gives you the lowest value. Prod gives you all the values multiplied together. Mean gives you what a mean is, sum them together and divide by the length. Variance, standard deviation, average squared distance from the mean. And the square root of that, and median gives you, if you lay them all the values out in a line in order and you chop the line in half, it's the value that is in the middle. You don't need to know how a median works, but there you go. And here are some other functions that I want to demonstrate to you, because these ones here all took in a vector of some length greater than 1, and they produced some sort of summary of it that was 1 value. Now in R, there's no such thing as just a single value. It's always a vector. It's just a vector that happens to be of length 1. So that's what they all produced. But then other operations will take a vector and they'll do something to every member. What's that called? Remember from the first session? That's vectorization. So these are functions that are vectorized. I could take the sign, and we can, because it's R and it's for stats and maths, it has bizarre, or at least it's interesting mathematical functions like arc, hyperbolic cosine. You can take the logarithm or the log 10. By default, R does its logs in the natural base E. Yeah, so lots of functions, and some of them are vectorized. Now, I told you functions take in things and give things out. Not all of them need information put in. In fact, I was just playing around earlier and found that sum apparently will produce 0 when it has no inputs, but date is another one. So there you go. You can tell when I'm recording this. Oh, I can give away some more of my private life. Here's the directory structure. It's the directory that I'm currently working in. Let's go for some more functions. Here are functions that make random numbers. So rnorm, R means random. Norm refers to the normal, the Gaussian distribution. This part here, previously I was giving it this variable called numbers or nothing. This is called the argument, right? The information you give to functions is called the argument, or the arguments if there are multiple. So the argument to rnorm I'm giving it is 1000, and that tells it to make 1000 normally distributed numbers. If I'm just going to save 1000 random numbers using that in a variable. I want you to note right now that I've named this variable previously. I've probably named variables using things like a convention like random underscore numbers. This time I've separated the words by using capital letters. So these are two common variable naming conventions that you'll come across a lot. This one's called camel case because the uppercase numbers kind of look like the humps on a camel. This one's called snake case to contrast it with camel case, I guess. Uses underscores. And people will tell you to observe certain conventions, and the conventions could be things like functions are named with snake case, and variables are named with camel case, for example. They're conventions. If people follow them and it's useful for them, then it's polite to follow them. That's advice for everyday life. If you think a convention is sensible and it's polite to do so, then just be polite. But it's just a convention. So now I'm going to run a function on these random numbers that I've generated. I've got 1,000 random numbers lined up here. The function, previously our functions output maybe a vector or a single value. This one creates a graph, and because RStudio is great, it actually facilitates the production of graphs. So rather than before RStudio, you probably had to produce this in a file and use another program to open it, but it just opens straight in the window here. So that's a histogram of those random numbers. The random numbers were following a Gaussian distribution, so naturally it looks like a kind of bell curve. Here are some other functions that are statistical functions that generate random numbers. Unif generates random numbers that are uniform in distribution. If I want to make the histogram there, I could do what I did previously and save a bunch of these numbers in a variable and then hand that variable as argument to hist. This time I'm just going to hand it in directly, because why not? Hist is expecting some values to work on. If it sees a variable name, it will unpack the variable and look in there. If it sees just values plonked in by another command, it will effectively do that. It's more complicated than that, but it will work perfectly well just to plug these sort of nested functions, if you like. Nested is in a nest, like a bird's nest within another nest within another nest, except birds don't make nests in other nests, do they? They lay eggs in there. So inside the nest is an egg, and inside the egg is a baby bird, and inside the baby bird are organs and things. And we could do this forever, but nested means going inside. So if we use that's our unif, we see we get a uniform distribution in the function. If we use rexp, we get an exponentially decaying distribution. If we use a Cauchy distribution, the histogram isn't very good at showing this, but you can Google the Cauchy distribution and figure out why. And there are going to be a few more random generators in a second, but we need another concept to build on first, and we're going to do that now. So, in advance of that, I really wanted to cover seeds. So, notice if I make a histogram of uniform numbers and I choose a low number of uniform numbers, like 10, then I can run these a lot of times and the histogram is going to look different. That is, of course, because if I run the random number generator twice, it's going to generate completely different numbers. This one starts with 0.7, that one starts with 0.4. Because they're random, why should it generate the same set twice? But I might want the random numbers to always follow the same, to always be generated the same. For example, if I'm doing a simulation study and I want someone to be able to replicate that study, this is why we use set seed. So we do set seed, and then we insert the days, or your favorite funny number. So 42 was hip when I was learning, and now 67 apparently is the new cool number to use in set seed. So if I set the seed like that, and then I generate 3 random numbers, okay, 0.91, 0.93, 0.28. If I set the seed again at the same seed, so it's using 42, and I run the 3 again, I get the same set of random numbers, and I can keep generating numbers, and they'll be random, but the moment I set that seed, it will reset to that 0.91, 0.93, 0.8. So that's how you keep your random numbers reproducible. Okay, let's queue up some more functions. This time I'm going to create a vector. I'm going to save it in a variable. I'm going to assign a variable. Let's use the lingo. Using the assignment operator, and the variable is going to contain a vector with the values 5 incrementally down to -5. There you go. Okay, sort. What's happened there? It's reversed it, so it's put them in ascending order. Absolute. The absolute value is just reflection about the number line. Take any negative value, make it positive. The range gives you. So here's a new output for a function so far. We've got a 2 vector. 2 vector is the hip way to say a vector of length 2. So a 2 vector, a 5 vector, a 10 vector. So you end up with a vector length 2 with the smallest and then the largest value. So I've got the analogy here that functions are like chefs cooking with a recipe. they take in certain ingredients and create a meal. I think I actually like that analogy better than they're a machine in a factory with inputs and outputs. If the ingredients are wrong, they'll either tell you that they're wrong, or that whatever the meal that they make is going to be pretty odd. So if I try to take the log of a negative number, we know logs of negative numbers are undefined. And look, it does produce a value. It produces nan. So this is kind of a special value that says not a number, or stands for not a number. But also at the same time, as we showed in the previous one, produces a warning. So it just says, hey Tim, usually when people run this and they didn't mean to, and you've probably messed up somewhere. But if you didn't, that's fine. I'm still going to produce you a value, but I can't produce you a regular old real number. So you're going to get nan. All right. So let's take this concept one step further. 5 to 1. If you sort that, it will sort it in ascending order. What if I don't want it to be in ascending order? I actually want to sort the number. I want to sort the list to make it descending. Now, just observe what happens with this weird thing. You can see this function now there's the first argument, and then there's a comma, and there's a second argument, right? So we've got multiple arguments to a function. If I run these two, the second argument, I've just given it true or false. It just says true. It says or false. In the first case, it created a descending order, and in the second case, it created ascending. So it's almost as if that second argument is sort of the answer to the question, would you like to sort this in descending order? In this case, it was true, so we do sort it in descending order. In this case, it's false. So no, this is going to be an ascending sort, right? So, this is, again, saying arguments give functions all the information they need, and there are often many arguments to a function. In fact, to make things simple in R, and as in many languages, you can refer to them by names. So traditionally, when a function takes a vector of numbers, or usually just the main thing it takes is very often just called x, but especially when it's a vector of numbers. And then the second argument is called decreasing. So if I type x equals 5 to 1, decreasing is false, it makes it more specific to the user. This also means that I can start to rearrange them, right? So I could type the decreasing is true, or let's make it false, so I can make sure I get the same answer, and x is 5 to 1. First, you get exactly the same result, but it means I've been allowed to twist them around, because as you've seen from the way I've taught it, they do have a default order. And if I mess it around and I put the vector second and the true false first, and let's make that 5 just to be consistent, then I'm going to get a bizarre answer. So here, in fact, it said decreasing the argument, decreasing must be a length 1 logical vector. So it's actually, it knows that if you don't give these things labels, it assumes that the first argument is called x and the second one is called decreasing. And in this case, it's actually said, hey, the thing you've given me for decreasing is a length 5 numerical vector, but it must be a length 1 logical vector. And we'll learn about logical values later, but true and false are logical values. Okay, how do I know what the arguments are? Well, I rely upon R's excellent help documentation. One of the quickest ways to access just the bits of this you want is you write the name of your function, you put the brackets there, which again indicate that it's a function, remember? The brackets are what indicates the function. I hit tab, and look what this RStudio is brilliant, isn't it? It knows to go and look up behind the scenes the help documentation and find the documentation referring to the legitimate values of different arguments. And it actually tells me x for sort is a numerical complex character or a logical vector. So you know what that is. I can give you another function that has a whole lot of different possible arguments. Write table, this is how you write a CSV if you wanted to write your data out that way. And it gives you descriptions of all the things. So that's very cool. Tab is, have a look at this. See how worn out that tab button is, because it's probably the most common thing I use on the computer, thanks to my R usage. And so if you hit tab when you've half written a command, so I've started writing sort, then I got lazy and I hit tab, it will actually give you the possible options to complete that command, which is wonderful for when you've forgotten the name of functions. I did write table earlier, so I did write, I hit tab, and you can see write CSV, write socket, write table, all the different possible functions. And in fact, I used a variable called numbers earlier, so if I hit tab after that, it will actually search in my environment for things I've defined and suggest them. Now, if you want the full help documentation, you just put a question mark before the name of any object that's got help documentations. It'll mostly be functions. So question mark sort, and then thank you RStudio. It's actually changed the tab here. It used to be on plots. It's changed it over to help, and it's rendered the help documentation in this wonderful format. So, and you can see it's got lists of the arguments, and then it's got some details that will, for example, tell you what sorting algorithm is being implemented under what conditions and things like that. It's got the references to where it's described. Here's the Donald E. Knuth, the art of computing. Look over here. Look there. I've got that right. I didn't even plan that. Cool, but there you go. The Art of Computer Volume 3, Sorting and Searching. So that's probably where a good description of the algorithm. Cool. Similarly, write table has a whole list of things like that. Okay, now let's go back to this concept of named arguments for functions and solidify that. Previously, we did things like. By the way, when I jump to the start and end of a line, I'm holding down tab and just pressing left and right arrow. So that's a lovely, convenient feature of RStudio. Previously, I did things like plotting a histogram of 1,000 random values. That's 1,000 random values. Plot the histogram, and I get it there. That was using a normal distribution. If I use a binomial distribution, rbinom, random binomial distribution. A binomial distribution is defined by a few more different arguments. It's got n as in the number of values I want to randomly draw, and because it's binomial distribution, it's got the size of the number of balls in the urn, if you like, and then the probability that each one is black or something, and the answer is the number of black balls that you pull out. Black and white balls in an urn. That's my favorite distributions. Are all describable in some variant of that. So. If I run that, I get the result of draws from that random distribution. RT, this is random from a T distribution. A T distribution is defined by a number of degrees of freedom. Similarly, a chi-square distribution is defined by its degrees of freedom. A Poisson distribution is defined by a rate parameter called you can call lambda. That's the number of cars that go past an intersection in a minute on average, but the number that go past in any given minute it will generally be distributed like that. Beta distribution, my favorite. You can make a beta distribution look like just anything else with these two very flexible shape parameters. Gamma distribution, Wilcox distribution, look into them. They're fun. So lots of distributions, lots of ways to do them. Right, let's play around with a concept that we touched on earlier. I mentioned that in a particular error message that a value was quote unquote logical, or that it was numeric, or there's an integer, different types of value coming into play. So let's look into that more formally and get an understanding. I showed you the function date produces a picture of the date. Now, what will happen if I try to add 2 to the date? So let's say, that's the date, Wednesday, February the 4th, and add 2, maybe we'll interpret that as 2 years, 2 hours, 2 seconds, or something like that. Oh no, it's actually thrown an error. So it says non-numeric argument to binary operator. What's going on here? We've talked about arguments. Arguments are things you give to functions. And we've also talked about operators. Operators were things like plus, divide. So what's going on here? These seem to be mixing two concepts together, right? It's saying that you've given a wrong argument, as in a non-numeric argument, to an operator, a binary operator, in fact. Okay. The penny might drop here and should that these operators are actually just functions. It's a cool way to write it. A binary operator, it's binary because it's got a thing before it and a thing after it. So those are the two arguments that go in. In fact, if I do 2 plus 3, I can actually here's a really cheeky way to write that. You can write it in a functional kind of notation. If you use these backticks, you surround the plus in these backticks, and then you can write it like a function. And the two arguments that go into the plus are 2 and 3. That does sometimes come in useful, but mostly it's just showing off. Okay, so the plus is a binary operator, and these two things are obviously of different classes. So it said it got a non-numeric argument. Now, the 2, that is numeric. That's obviously a number. So, and this one isn't. But how could I know that for sure? Well, I can run the class function. It will reveal what the type is. So you can see that a 2 is a numeric thing, and that today's date, that's a character thing. It's just a string of characters. It doesn't inherently have any numeric value, so it doesn't work. If I put an L after the 2, this is how you tell I explicitly want an integer here. You may well do this when you work with really big data, because just for the reason that an integer is stored differently in the memory, and that means it can be processed differently by your CPU, for example. And because it's stored in a different and simpler way than a regular numeric value, it's faster. So a numeric value is stored using a convention called floating point, and floating point arithmetic takes more processor operations to do than integer arithmetic. So yeah, if you just put the L after there, it forces that value to be an integer. Letters is a bunch of letters. If I look at the class, that's character. You'll notice that all the characters just are notated in the print function by having quote marks around them. Indeed, when we want to define characters ourselves, we just put quote marks around things, and that will automatically be defined as hello, a character vector, just like that. Okay, and the reason I include a thing like this is obviously a numeric value. This is, as we saw, that's going to be forced to be an integer value. When I do an operation on them, I'm going to get a value back. So that's numeric, and the answer, and obviously it has to be, because it's got all these decimals. If it's going to be accurate, it's going to have to be stored as a numeric. But this is just to make or raise your consciousness to the fact that R is making decisions for you all the time. And this will absolutely become important later in your code, that are sometimes the decisions are obvious and logical, other times they're pretty ambiguous, and sometimes you don't even get a warning. So let's see. Okay, here's another function. The function is paste. Now paste is just a concatenator of strings, so it takes 2 separate character strings and it puts them together. You can see the quotes at the start and the end, but this is just a space character, which to the computer is just like any other character. We call them white space characters. If we add another argument, a named argument called sep, this is the separator. So we told it we're gonna put them together with an underscore. Now what happens if I do paste, but I'm not going to give it character strings anymore? I'm going to give it integers. So this function is obviously designed to concatenate characters together. Is it going to produce 123? No, it's actually going to convert these things, okay? Convert them into character strings, and you can tell because of the quote marks. And I just put this example because I think it's cute that class itself produces something that you can run class on, and it's a character. All right, for our next set of exercises, we are going to need to create some vectors. So the vector creation function is just called C. C is short for catenate. It sort of means to put things together in a row, in a line. And I've put in a whole lot of character entries. This character vector has 6 entries. That's V. If I ask what is the class of V, it contains characters. Notice that a vector, it will contain multiple entries, and all the entries have to be the same class. We'll work later on cases where you want to save. You want to work with items that have multiple different classes contained within. Okay, so I need to do this demo. I need a vector that's integers. I need a vector that's numerics. I need a vector that's characters. So let's look at these 3 classes: integer, numeric, character. I've got exactly what I wanted. Now let's catenate 2 of them together to just further explore how R converts things. I create an AB. It combined integers and numerics. The class, what does it do? It usually it sort of takes the most inclusive class of all the classes it's got on offer. So it's converted them into numerics. If I include the character vector in that catenation and look at the class, it turns into a character vector. And you can in fact tell when I print the vector, it's taken all these values, the 1, 2, 3, the negative 4.54, and it's put quote marks around them to indicate that these no longer have numerical meaning per se. They are now just strings of characters. So R is converting stuff behind your back. Good. That's kind of wraps up that section. We've got two more little... No, we've just got one more short section to go, an introduction to indexing. So make sure you understand everything so far. Have a pause or whatever, and let's jump into this last section. So for this one, again, I need a vector. I wanted a slightly longer one. I've given you a poem by one of my favorite authors and comedians in the world, Spike Milligan. There are holes in the sky where the rain gets in, but the holes are small. That's why rain is thin. Pretty silly. Wrote lots of poems for kids. I think he wrote them for his children. Okay, now that's a vector. You can see that each entry, there are 19, 20, 21 entries. What if I want to just pull out one particular entry? The answer is I use another operator. This is called the indexing operator. It's just the square brackets, and they have to be one bracket and the other together. And I can put in the number that corresponds to the bit that I want. So, and the numbers start at 1. That is not universal to all languages. Very often they start at 0. In fact, I have a preference for that, but you know, it's R. And there are some nice things about starting at 1. It's sort of pretty naturally intuitive, I'd say. There are holes is number 3. So if I run that, I get holes. I can actually select multiple parts. So if I give it a vector that asks for the first entry, then the 10th, then the 2nd, then the 12th, you'll get them, and they'll be in that order. So the first entry, 1, there are holes in the sky, and then the third entry here, 1, 2, 3, is 2. So it's going to give us the second entry in the third position of the vector that's output. Okay, I could use my that vector creation operator, the colon, that will give me the first 11 entries. Have a guess at what this is going to produce. So this one gave me 1 to 11. This is going to start at entry number 12. There are holes in the sky where the rain gets in, but, I think is the next word. So it's going to start at but, and then it's going to go to what? It's going to go to the length of the poem, to whatever the length of the whole vector is. I think that was 21 earlier. Let's just have a check. 21. So it's going to be the values from 12 to 21, and so it's effectively just going to give us the rest of the poem. What about this one? I use that vector creation operator. This time we're going from the length of the poem 21 to 1, so it's going backwards. We showed in this example that the output vector is not going to be sorted or anything. It's just going to give you the values as in the same order you requested them. So that's going to be the poem backwards. Thin as rain, why that's small are holes, which is actually quite a good poem in itself. What happens if I do something really sneaky and I try to mess around with it? And I'm going to give it a value that, you know, the indices are clearly meant to be integers, 1, 2, 3, 4, 5, up to 21. I give it a decimal. Okay, it's given us there. So that's the first word. So we can tell, firstly, notice it hasn't thrown an error. This is the kind of thing that I would say you should throw an error, but, you know, doesn't always. And there are some reasons why. Sometimes you do just want this kind of behavior. And you notice that it's rounded down. It hasn't rounded to the nearest integer. If it rounded to the nearest integer, that would be 2, and it would have given us the word R. But no, those are decisions R makes, and because, as I said, we want to learn R deeply and fully, we need to have a familiarity enough to at least be asking the questions and be conscious of when it is that R's making decision for us. Okay, so I previously showed you the random uniform function. The first argument tells you how many uniform numbers I want, and I've added some more arguments here. I've put in a min and a max, so you can kind of guess what this is going to do, right? It's going to give us random uniform values between 1, the min, and what's the max? Is the length of the poem, the length of the entire poem. So if I run that, that's going to give us those random numbers, and then as we saw, if numbers are not whole numbers, they'll just be rounded down. So if I run this as the index, it's going to give us a sort of randomized poem, just 100 random words extracted from that poem. And last one for today, we're going to learn the legendary seek function, which we use all the time. Seek and rep is another one you'll see come up soon, and we just use these constantly. Seek makes sequences of numbers. So I've written 1, the first argument is 1, the second is the length of the poem. You may have guessed this is going to be a sequence of numbers that starts at the number 1 and ends at whatever is the length of the poem. If I hit tab now, seek was a bad example because it doesn't, for some functions, for reasons that we'll get into later, they're not documented in a way that's accessible to that tab function, but you can always find information by pulling up the full help using that question mark. So from and to are the first 2 functions, and then by is the third, and I've actually named the third explicitly just to be clear. By 2 means it's going to go in jumps of 2. So a sequence from 1 to the length of the poem in jumps 2, that's going to be 1 through that and end at 21. So effectively, it's just giving you every second word in the poem. I hope this has given you something to think about. I hope you've enjoyed learning these functions that we'll expand on in the future. I am Mark Timothy Rabanus-Wallace, and I look forward to seeing you in the next one.